So, hello again. Welcome to our webinar production review of a special grade alloy steel in Egypt, arranged by AIST organization MENA chapter. Uh, Before I start, I have some announcement. I need to say it to you. So, please don't discuss with other your own or competitor prices procedure or anything that might affect price such as cost, discount, term of sale, profit margin, or anticipated wage rate. Don't make a statement about your own prices or those of competitor. Don't talk about what individual companies plan to do in particular market or with particular customer. All attendees were muted during this event. You have opportunity to ask a question through question and answer. So you will have in your screen, you will have a space to write your question. We will make sure to ask your question to the speaker. And if we are not able to do it because of the timing, we will answer in email and we'll send this email to you. So if you have any question, feel free to write your question in question and answer section, I believe in your right hand in your screen. This is a live session and is being recorded for distribution to register attendance. We'll be able to have also approval to share also the presentation, the slide in PDF format. So it will be in our AIST website afterward. If you have any technical difficulty, please contact chapter@aist.org and they will be able to help you during the webinar. Today, we have four speakers. We have Dr. Iman al-Mahallawi from Cairo University. We have Mr. Engineer Ahmed Hammam from Arco Steel. And we have Dr. Taha Matar from Galala University. We have Dr. Kristen Redier from Intico Company. And my name is Ashraf Hanna. I'm moderator here and I'm licensed professional engineer, Ontario, Canada. I start my work in AIST Steel in Egypt and then Rush Steel in Saudi Arabia. Then I moved to Canada and now I'm working in RHI Magnesita. Let me introduce the first speaker, and I'm so happy to introduce Dr. Iman al-Mahallawi. She has a famous name for all people work with metallurgy or material or steel industry. She's a professor of material and metallurgical engineering at Faculty of Engineering, Cairo University, professor of mechanical engineering department in British University in Egypt. She got his BSc in engineering Cairo University in July 1981 and master degree from Cairo University too in 1983. And after all 4 years, she got her PhD from University of Leeds. Her main job is teaching undergraduate and postgraduate classes, leading research group, writing research proposal, reviewing activities, journal, books, conference, workshop, and articles. She's offering also consultation to more than 50 Egyptian industrial and service facilities on manufacture failure analysis, material development, risk analysis, and management and material validation. Conducted research and industrial service relevant to metallurgical industries, member of Student and Quality Assurance National Committee. She's a leader of many research groups on topic in the field of steel making, foundry, manufacturing, and heat treatment research group in advancing alloy and material and nano disparate composite research, renewable energy material research group, sustainability of material renewable energy project. So let's welcome Dr. Iman. Please start.
Okay, thank you very much, Ashraf. And I'll share my screen, just a minute, okay. Okay, so first of all, thank you very much. I would like to offer my great thanks and appreciation to the AIST, the board members, and the supporting staff, Jill, Stacy, and Brian, for organizing this event. We have been looking forward for it for a long time in Egypt. Second, I would like to thank all the attendees as well for attending this webinar. I hope they benefit from it. So I have been asked to present the first lecture or the first presentation on this event and give some ground or background on the metallurgical concepts of alloyed steels and their applications. So first of all, what is alloy steel? Alloy steel usually refers to a group of steels which are beyond the conventional carbon steels that we know, where special alloying elements are added. We all know that each alloying element has a certain benefit or a certain advantage when added to steels. So actually what happens when we add these alloying elements is that the steels gain or render more specific properties which are much higher than the original low carbon counterparts. Just a quick look. For example, copper is added for the sake of corrosion resistance within a certain range. Nickel is usually added to increase the toughness and improves corrosion resistance as well. Chromium, molybdenum, and vanadium, they are what we call carbide formers. And apart from forming the hard carbide, they also contribute towards the hardenability of the steels. We have also manganese, we have silicon, which are or do exist in conventional steels at certain smaller amounts, but we can also make use of them and use them as alloying elements. So the background of the alloying elements and their addition to steel is something, it's always related to a certain range. We have to understand this very well, because within this range, these alloys are of benefit. But if we exceed the range, we may have some problems or some counterbags coming or resulting from the increase of their percentage. Generally, when we talk about alloy steels, in addition to the main definition, in which we have just said that they contain other alloying elements, we can designate or classify them into different groups. We have the conventional low alloy steel, which usually refers to those steels or iron carbon alloys with ranges of alloying elements less than 5%. And we have the high alloy steel, in which we add higher than 5%, maybe up to 50% of those other alloying elements. But I say up to 50% because, of course, the remaining has to be 50% iron, because they are still called steels. Otherwise, they would be called something else. For example, if nickel is higher than 50%, then they will be no longer steels. Actually, during the last decades, we had some additions to these conventional family of alloyed steels, where we had, for example, the high strength low alloy steels. These were introduced something like 30 or 40 years ago. And the idea was just adding minor amounts of alloying elements, not as high as the 5%, but less. And we still can get higher strength, especially for construction applications. Not only that, we had other advances that have appeared and are still having research currently, like the advanced high strength steels. And these are special tailored groups of steels based on the conventional groups, but we tailor their properties by other methods apart from alloying elements, just like the heat treatment, for example. The maraging steel also is a well-known group of alloyed steels. And of course, we have the tool steels. The tool steels are divided into a number of other types, like air hardening, water hardening, oil hardening, high-speed steels, and hot working and shock resisting steels. And of course, last but not least, which is the most important and most well-known among the engineers, are the stainless steel groups with their groups of martensitic, ferritic, austenitic, and duplex alloy steels. So this is from the scientific point of view, designation based on alloying elements and content. we cannot skip the importance of designation. We have to understand the grading system because many of the engineers working in the market, they know steels by their designations. There are many designations, of course, to describe the alloyed steels, but we shall focus on the AISI grading system given by the American Iron and Steel Institute and the Automotive Engineers Society of Automotive Engineers, the SAE. And this is the one that most of us would have learned during their engineering studies at the university. So it is a numbering system. The designation is a numbering system where you give a certain number. Usually the first number from 1 to 9 would refer to the type of the steel. And then you have 3 digits where the last 2 refer to the percentage of the carbon, and the second one after the 1 would describe to the other alloying contents in the steel. Usually the grading of the 1 would be the carbon steels, 2 would be the nickel steels, 3 would be the nickel chromium, 4, which is very well known and common in the market, are the molybdenum steels, and then we have the chromium steels 5, 6 are the chromium vanadium steels, 7 are the tungsten steels, 8 are the nickel chromium molybdenum steels, and 9 are the silicon manganese steels. Of course, each one of them has a certain range, as I have just mentioned, for the alloying elements. When we say manganese steels or nickel chromium, there is a range, and these ranges are all available on the standard specifications. And now we can understand why do we have limitations on these ranges, because we obtain the benefit that we want or that we are looking for through this designated range. However, in this context, I would like to say that maybe we shall need the standards should be revised during the next decades because the steel industry has moved from producing steels from raw iron to using recycled steel, and recycled steel is usually associated with some deviations in these contents and ranges. And still, it's a very hard decision. If you are a maker or you are a manufacturer, are you going to throw away all your product just because something has exceeded 0.1 or 0.1 or whatever of these contents? And this is an ongoing research by many researchers on seeing or checking how could these deviations affect the properties that we are looking for. Some of the important example, for example, in the market, the groups 43, which are, we have just mentioned that the 4 would be the nickel chromium groups, and then we have 4301, 4330, we have 43 BVX, 4781. I mean, these tables will be available at your hand, and they just give you some examples of the well-known types of steels in the market that are used for a variety of applications. Again, this is for the chromium steels, the 5 XXX groups, and the chromium vanadium, tungsten steels, and whatever. So the stainless steels are included, as I've just mentioned, in the AIST steel specification range, identified by the 3-digit numbers, each with a unique characteristic. The stainless steels, they have another grading system, also in the AISI, where we have the austenitic stainless steels, and usually these are characterized by obtaining nickel and chromium, both nickel and chromium, and the structure would change to be an austenitic austenite. Of course, in this reference, there is no time to review the iron-carbon phase diagram, but we all should remember the iron-carbon phase diagram, where we have learned that iron with carbon would have would be a ferritic or perlitic or whatever. But when we add the alloying elements, we would have changes in this typical microstructure of iron, and we can promote the formation of other structures or phases, just like the austenite is promoted with a certain addition of nickel and chromium in a certain range. And we have the well-known austenitic stainless steels, which are famous as well for surgery applications and for home utensils and many other applications. Ferritic stainless steel grades are a little bit harder and stronger than the austenitic stainless steels. They are used for many engineering applications as well, and they would contain higher content of chromium on the expense of nickel, because nickel is an expensive element. So when we need higher strength and maybe different corrosion conditions, we can use them. We have also the heat-resisting chromium alloys for high-temperature applications, martensitic precipitation stainless steels, the 600 group, and the precipitation hardening groups, and the duplex stainless steels as well. So we have many, all these are different different alloy steels. In stainless steels, we should not forget that we have another suffix at the end of the number, which is LH, F and PH, and usually this refers to, for example, the L would be low carbon, extra low carbon, and the H would high carbon content, and the F will indicate the steel is free machining, and the PH stands for the precipitation hardening groups. So actually, this was regarding explaining the designations, and usually the designations are provided or developed by big institutes and societies. On top of them are AISI, the ASTM, the ANSI. Actually, they are leaders in making and developing the grading and designation system for the alloy steels. And of course, we all know the standards and the standard specifications that we have to abide to in validating steels for applications. And here you'll find, for example, some examples again for the steels and the ranges of the alloying elements that can exist on them. In this context, in addition to what I have mentioned about the alloying elements, we have to notice also that the two elements, sulfur and phosphorus, are two elements which are undesirable. We rarely add them to steels except for special conditions when we need, for example, machining or machinability, we may add some sulfur, but usually they should be kept as a very low value or a very low concentration or percentage. And this is the challenge with the alloyed steels, because in carbon steels, we may have a wider or more generous range for the sulfur and phosphorus than the alloyed steels. And because their harmful effect is pronounced more and more on the properties of the alloyed steels if they are present in higher than the required values. For example, you can see here, for example, it's 0.03 in some of them and 0.15 in another. So, I mean, we have to abide to these concentrations. Usually, these are not alloying elements. They are harmful elements, or what we call tramp elements, and they should be avoided. Some of the steels, like the contents like the manganese and the silicon as well, should be kept within the designation or the required, those required by the designation, because if they exceed their content, then they will be harmful again to the main properties that we are seeking. Now, why are we talking about this? I mean, what's the importance of having alloying element content or microstructure or phase or whatever? What's the importance of that? The importance is to obtain the properties that we are looking for. The most important properties that we are looking for when we talk about alloyed steels usually are high strength, toughness, ductility, corrosion resistance, wear resistance, and this would be associated usually with some characteristic in other properties like thermal conductivity, specific heat, electrical resistivity. But usually engineers think more and more about the mechanical properties, but they should not forget that, number one, that the mechanical properties, sometimes if you increase the strength, the toughness is deteriorated, and this may have an effect on other physical properties, and they should not be overlooked according to the application. Again, here we have some other examples for some important groups of steels and their applications. And of course, these applications are based on the properties or the requirements. So we have the group 1010 would be used for the automobile panels where we don't need very specific strength. 1020 for pipes and structural steels. A36 for structural bridges and buildings. A516 for which is grade 70 for low temperature pressure vessels. And then we have the high strength low alloy steels, again the A572, A633, and A656, and they are used for bolts, bridges, structures, track frames, and other applications. So each application, in many occasions, the designation would identify the specific steel type used for a certain application, whether it is valves or bridges or construction or low pressure vessels or whatever, depending upon the required property relevant to this application, whether it is high strength or high strength with high toughness, or high strength with a certain amount of toughness or ductility. So according to these requirements, we would designate which steel do we need to use. Crankshafts, bolts, chisels, hammers, knives, hacksaw blades, all these are engineering applications where we need to use alloy steels. And when I've just mentioned at the beginning, for example, at this table, you can see a comparison between the conventional carbon steels on the top, starting with the one used for crankshafts and bolts, chisels, hammers, knives, and hacksaw blades. On opposite to the well-known alloy steel, which is common in the market here in Egypt, people know it, 4130 or 4340 or 6150, which are used for more severe applications for gears, bolts, axles, bushings, shafts, pistons, and other applications. And actually, that's the driving force. Why do we need alloy steels? And that's why we have we are glad to have this event to tell and inform the market that we need alloy steels as much as we need carbon steels as well. Again, here, this presentation just includes more examples for different conditions. And maybe the new thing appearing here is the word annealed. And actually, when we talk about alloyed steels, we should not forget that alloy steel is not only a matter of alloying elements, but the heat treatment is a very important challenge to achieve the required properties. You can never achieve your property just by having the recipe for the chemical composition. You have to have the controlled heat treatment. And the most interesting thing is that you can have a wide range of properties depending upon the heat treatment. From the same composition, you can have strength no more than 400 megapascal. Controlled heat treatment would make you achieve strength more than 1000 megapascal. The whole idea about AHSS, which is the advanced high strength steel that I mentioned at the beginning of the lecture, is just control of heat treatment. Simply control of heat treatment. You can double, triple, and quadruple the strength properties and control the strength with the toughness, because we all know that when we increase the strength, this is done on the expense of the toughness. But you can control the strength and the toughness, both of them, to exceed very high values just by controlling the heat treatment. And in this context, we should have a little bit of revision. We always need to remember the science and technology of heat treatment, which includes several processes such as annealing, quenching or hardening, tempering. Now we have other treatment like quench partitioning, and we have binetizing, and a lot of other non-conventional ones apart from the three that we have learned at university, which are the hardening, tempering, and annealing. Of course, this picture is just for showing the whole range of alloyed steel that we can obtain by applications obtained or achieved by alloy steels. So what is the challenge? I mean, if it is so simple, so what's the problem? Why can't we produce it? Actually, the challenge in producing and manufacturing alloy steels is associated with the production process. The production process is not as simple as the carbon steels. Some steps are just common, like the charging, using the electric arc furnace, chemical analysis, and the refining in the ladle furnace. But then you need to have to charge the alloying elements. You have to calculate and make calculations for the right alloying elements. And then you have, in many occasions, you need to have vacuum degassing step, because you have to eliminate all the sources for entrapment or for tramp elements presence. You have to get rid of the oxygen and the hydrogen and other things that may get into the steel. You may need wire feeding, you may need argon gas rinsing, and actually other processes before you pour your product and take it to either the continuous caster or to the forging process or whatever. So we have one challenge during the melting and production process, and the other challenge is during the heat treatment. If the heat treatment is not controlled, you do not get the properties that you opt. Of course, the manufacturing and the heat treatment would be manifested in a microstructure, which make us achieve or reach the properties that we are looking for. And that's the trick about why do we need to talk about microstructure and chemical content and heat treatment procedure and all these things, because you can never get what you want without controlling the microstructure, which is the main phases we know: perlite, benite, martensite, ferrite, duplex, whatever. I mean, all this has to be achieved. So this manifestation is actually obvious in the new grades of steels. We had the first generation of steels were highly ductile, but the real strength was low. Whereas the second generation, we could achieve high yield strength, but on the expense of the ductility and the toughness. The third generation steels that now are investigated and actually in the market, which are like the TRIP and the TWIP, transformation-induced plasticity and twinning-induced plasticity, quenching and partitioning. I mean, all these groups of advanced steels, actually, they can achieve strength and toughness actually exceeding 2 times the conventional types of steels, despite the fact that they are based on the same chemical analysis. Just a quick reminder of the heat treatment processes that we have learned earlier: annealing, normalizing, hardening, tempering, mar tempering, and AIST tempering, benite forming, and actually all these should be kept in mind when we plan for producing alloyed steels of special properties. Again, a flow chart just for as a reminder for those who have forgotten heat treatment. And of course, the phase diagram is important in this aspect. Here is an example for a typical heat treatment process for alloyed steels, where you can find that you need 2 stages actually of hardening, 2 stages of cooling and tempering in many of the applications, unlike conventional carbon steels where you do not need this stage. Other examples for different alloys. Okay. Maybe mar tempering and AIST tempering are not very well known, but they just mean that we temper in the range of martensite or we temper in the range of austenite to achieve the microstructure that we need. We always also have not to forget that sometimes over tempering may produce some defects, because we have secondary carbide formation, which may harm the toughness of the material. So we should actually control not only the hardening stage, but also the tempering stage for achieving the required properties. And here are the references. Sorry, I had to be very fast so that I do not exceed the 20 minutes. I hope I'm in time, and thank you very much. And I'm at your service, Ashraf. Please let me know what should I do now. Thank you.
Thank you, Dr. Iman. This is really very, very good presentation. It's remind me with a lot of stuff from during studying university. I have a question for you. So in the United States of America, there is a trial to make something called high strength steel. This mainly for automotive, to use like very thin sheet, light sheet, and to be used in automotive industry. Can you give us explanation what is this is high strength steel, and what is the idea to can approach this high strength steel in industry?
Yeah, of course, doctor. I do not live in the United States, so I know that these advances are happening, and this is the group that they call generally AHSS, which is the Advanced High Strength Steels. And the idea here is that you control the heat treatment and the chemical analysis in such a way to obtain, for example, transformation-induced plasticity. Means that you develop some alloys by controlling the alloying elements and the heat treatment, so that you may have, with hits or with deformation, you will have extra properties added. Instead of losing the property, you will have additional properties through transformation. One phase transforms to the other. Very simply, just like the Hatfield steel. What's the idea of the Hatfield steel? Is that the manganese, when you put it in high content and you use it for wear, for example, during the wear, instead of the material wearing away, the material strengthens because there is a transformation happening on the original microstructure of the stainless steel on the austenite or austenitic phase, on the austenite phase to martensite. So this is the idea here, is that we control the properties so that we would have hardening phases. We know the hardening phases are the martensite, the benite, and if we can control a microstructure which contains not only ferrite and perlite, or not only martensite, because ferrite and perlite on their own would not be very strong. And then we have on the other side, martensite is not tough. So if we can control the microstructure to contain more than one microstructure, you will benefit of both. And that's the idea behind the TRIP and the TWIP, which are actually developed for the automotive industry for having higher strength combined with higher toughness or ductility.
Thank you very much.
I could answer.
Yes, very good. Actually, I have another two questions, but we don't have time. But I will give you just question for half minute. From Harun El Fassi, he asked a question about it is possible to produce high strength steel and stainless steel without vacuum degasser?
No, actually, unfortunately not, unless you just melt it. If you just use the same raw material and you melt it in an induction furnace, just like the foundry, what the foundry does, this is possible, but you cannot make a recipe and produce your own product by mixing a charge and obtaining it without a degassing process. And actually, sometimes you need slag refining. Refining process is not very easy. I don't think it's possible unless actually you are really just casting a product in a foundry where you remelt a scrap which is identical to what you want to achieve.
Yes, this is right. Yes, so it is impossible. So far, it is impossible in industry to produce high strength steel or stainless steel without vacuum degasser. For now, technology. We don't know the future, but for now, technology is not possible. Okay, thank you very much, Dr. Iman. We'll go for second presentation. Please stop sharing.
Thank you. Thank you very much. Thank you.
The second presentation let me introduce the second speaker here is Mr. Hammam. Mr. Ahmed Hammam, he's the director for Arco Steel. He got a master's degree in metallurgical and production engineering from Alexandria University. His project title was Controls the Mechanical Properties for Hot Rolled Steel Product. He has 30 years experience in the steel industry, served biggest steel producer in the Middle East. Between 1989 and 2001, he served as a senior engineer and section head at AIST DK in Alexandria, Egypt, working as production control for direct reduction plant and mill shop, followed as rolling mill production head for designing for pickling line for flat product. Between 2001 and 2004, Hammam made a startup for 2 rolling mill as a plant manager in Bishai Steel in Sadat City, achieved high performance record after first year of startup. Till 2017, he served as a plant manager in Rush Steel in Saudi Arabia, in Jeddah, and established 1 million ton annual production plant from design phase till the achievement plant capacity with a smooth and efficient operation and startup. From 2017 to 2021, he is rolling section manager in South Steel in Egypt, and from 2021 till now, he is a manager director of Arab company of special steel, which is Arco Steel in Sadat City in Egypt. Hammam has very good experience, and his experience reflected to publish 3 articles and technical paper in the field of rolling mill technology. Let's welcome Mr. Hammam. Hey, Mr. Hammam, you are muted. So turn your computer, turn your camera and share your screen, please.
Hello.
Hello.
Thank you very much for this webinar and all the organizer for this one, especially Mr. Ashraf. And thank you very much for Dr. Iman for the interesting presentation, which is very good for as a presentation, starting to my speech also about this subject. Now I will share this one. Shared now?
Yes, put it in a presentation mode.
We'll speak now about the overview of product portfolio for the alloy steel, as well as the production challenges at Arco Steel, which is the company specialized in producing bar and wire rods, special steel in the Middle East area. It is only the company which is established since 1998. First of all, we will speak about what is the special steel. There was a good introduction done by Dr. Mahallawi. When we are speaking about the definition for the special steel, to be clear for everyone, it is the target to have the clean steel of gases and non-metallic inclusions. And this cleanliness should be done through the starting from the scrap till all the production procedure until reaching the final product to be suitable for heat treatment, to reach the actual desired mechanical properties and grain structure, which is already specified from the end user, because special steel always going to the end customer for its special application. If you are talking about the main characteristics of a special steel, first, as normal, is the chemical composition. The special steel, for each kind of steel, we have to control strictly the chemical composition for every grade. And some grades are very, we can say that, very large for the end customer. Then they are asking to have this one in a tight, specific limitation for some items. So it should be considered because it's affect its final application. At the same time, you have to control the trump element due to its bad effects, especially the phosphorus and sulfur and copper. And this is could affect the final application and giving bad results for reproduction again. The main point for the special steel is controlling the dissolved gases, which is mainly the oxygen, nitrogen, and hydrogen. If you are putting the normal values for this one according to standard, it's oxygen is around 15 ppm, and nitrogen around 70 ppm, and hydrogen is approximately 2 ppm. But for getting a very good results for the post-heat treatment, we have to make more strict for the levels of such gases, especially like the nitrogen. We are trying to keep this one maximum 50 instead of 70. And for the H2, we are targeting 1 ppm. So this is can give the answer for the guy who asking about can we produce the special steel or alloy steel without vacuum degassing? The answer clearly is impossible unless you can make this one in the induction furnace by melting the same steel and got it in the other form. So in order to control the dissolved gases, you have to have the vacuum degassing. The second point for characteristics of special steel is the mechanical properties, which should be controlled according to the specific applications. Always you are saying in special steel is a specific application, because you can produce the same steel grade suitable for more than application. And this variety for application giving a limitation for each component of the chemical analysis, and also for final mechanical properties like the tensile, hardness, reduction of area, toughness, impact toughness. All this is controlled and giving the results appropriate to the end customer. The third one, which is the microstructure. We have to be very keen to keep the grain size and the shape of the grain size in a manner that there is no distortion for this one, and it should be according to the ASTM standard from 6 to 12, and also definition for the grain size should be controlled or according to the final application. Always you can say final application is the master key to be succeed in a special steel. The second part for the microstructure is the non-metallic inclusions, and should be in a higher degree of quality. We are keeping the standards of K3 approximately equal or less than 20. The structure should be adjusted even during the production on line itself, or after by the heat treatment, in order to keep the desired microstructure with the desired grain size. If you are looking to a plant operating special steel, first of this one, we have to be keen about the scrap segregation. Because the scrap segregation should be done according to the chemical composition of scrap and the desired steel grade we need to produce. So we have to have the scrap divided into stainless steel scrap, high manganese scrap, high chrome scrap, like this. It should be segregated well. And if the segregation is done well and very arranged for each steel grade, then the results will be much easier in the electric arc furnace. After that, the electric arc furnace, normally you are get rid of the phosphorus and sulfur, and after that, putting the steel in the ladle furnace. In the ladle furnace, where we can control the chemical additions for the different alloys in order to reach the desired final chemical composition. After having this ladle furnace, we are going to the vacuum degassing. After the vacuum degassing, the pellet is coming from the CCM machines, which is considered also some items to be considered for the casting. It's a closed casting for the special steel. One of the main points to control and succeed in producing the special steel alloys, you have to make the reconditioning for the pellet. This means that the pellet is not just coming from the melt shop, going to the rolling mill, and then reheating again and doing the rolling. No, but you have to take care for the pellet. In special steel, starting by making the shoot blasting for the pellet, and also there are MBI by Eddie Carroll, also inspection for the pellet to ensure that there is no any defects can affect or propagate during the rolling process. Also, we are doing the grinding for the pellet. This grinding done by manual grinding or automatic grinding. Then the pellet is transferred to the reheating furnace, followed by the rolling stands, normal rolling stands. For our case, we are producing bar mill in 22 stands, and in addition, we are producing the wire rod in 32 stands. After that, the finalizing the final product is going for straightening machine. The straightening machine to ensure that the bar is highly straightened according to standard, because it's going for a very dedicated application. Followed by the straightening one, it should be inspected and getting results for the inspection by the eddy current for the surface defects, and the internal defects by the ultrasonic. According to that, every bar is released. And for special steel, the conditions is every bar should be tested by this one. No bar is going out for special application unless inspected by the eddy current and the ultrasonic. After we got the total layout for a plant who is producing the special steel, we'll speak about the special equipment. As we said, the first thing was the scrap segregation. The second thing is the pellet reconditioning, because the pellet conditioning should be done by the shoot blast, which is very essential to avoid any unclear surface defects, and also to avoid the scale, because the scale also intervention during the rolling process causing some surface defects. So it should be like this. The online magnetic particle inspection MBI should be done for this one, and the automatic grinding or manual grinding according to the case of the pellet. The pellet, if we're speaking from the in, we have to speak about the out, which is meaning after the final product, we can make all the post-heat treatment for the material. And this one, we have around 3 kind of furnaces, which is the first one is the solution furnace for the treatment by the annealing austenized stainless steel. The second one for the bogey furnace for the annealing, normalizing, and tempering, alloy and spring steel and others. The last one is the quenching and tempering, which is giving the good results according to the special application, especially for automotive industry. For this one, we have the quenching and tempering, and we can do also annealing for the austenite stainless steel, the normalizing, stress relieving for this one, to ensure that by the induction we are getting the constancy of the structure and the mechanical properties along the bar cross section and the length of the bar itself. The main task, I think, is the vacuum degassing and the continuous casting. These, which is the 2 items, which is we can say it's the critical 2 items in special steel production application. For the vacuum degassing, as you see from the picture here, it is the ladle after the LRF. Then the cover should be put above this one to be isolated from the atmosphere, and then starting the cycle for doing the vacuum inside this ladle by kind of mechanical pumps in order to reach a pressure around 1.3 millibar. By this one, we are keeping, this is around, to reach to this stage 1.3 millibar, it takes around 6 to 7 millimeter. After that, we are keeping the ladle under vacuum for around 20 minutes. And the total duration for vacuum degassing is around 30 to 31 minutes in order to reach the conditions which is controlling the gases for the hydrogen and nitrogen and oxygen also. Then start to release the pressure again by the nitrogen and make purging until reach to the normal atmospheric pressure. Then the material is already, we ensure that it's coming to level of gases suitable to casted to got the desired quality. The samples should be taken from each stage of this one. Something say normal for the furnace, for the ladle furnace, for the vacuum degassing, from the ladle. Every stage we have to ensure that the samples are taken and the results are according to standards. After that, we are going to the continuous casting machine, which is starting by the molten steel in the ladle. So it should be a shroud between the ladle and the tarnish, and also another shroud up to the mold. So it's a closed casting procedure. By this one, we can control and ensure that the final results will be in a good conditions, followed by the first and secondary steering in the mold that to keep homogeneity for the final one. Now we got the materials that we already nominated according to the standard and produced for these steps. If we can get here the same, which is already presented by Dr. Iman in the previous presentation for the material. And here we are speaking about the carbon steel and alloy steel. 5% is approximately the ratio for low alloy and high alloy percentage ratio. For the carbon steel, we have the high carbon steel, medium, and low carbon. This is examples for the grades, which is classified according to some applications. So this one for the alloy steel grades, the different kind of steel grades: 42 chrome moly 4, 34 chrome nickel moly 6, 30 chrome nickel moly 8, 16 manganese chrome 5. All these depend for this as a alloy steel for special application. The carbon steel grades, which is S355 J2, which is commonly used for a lot of applications in the automotive, C45 and 70 manganese 20. The wire rod steel grades is slightly different because it's reached into up to the ISI grades 1085, 1075, used for the wire drawing applications like the sleepers for the railways, used for the strands also, and this wire application. The free cutting steel grades should be controlled, and the free cutting always we are depending on increasing the ratio for the sulfur, which is known. Also the grades of tool steel like 56 nickel chrome moly V7. This is one of the famous tool steel grade. The bearing steel 100 chrome 6, which is is a critical one to reach casting under 1% of carbon. The cold heading and cold extrusion steel grades also, it's produced. The spring steel 55 chrome 3, which is normally used for the automotive spring plates, 60 chrome 3 also. The products are divided into round bar, which is produced in Arco steel from 60 millimeter up to 140, and the square from 80 by 80, 90 by 90, 100 by 100, and the wire rod sizes from 5.5 up to 16 millimeters. And the application for this one for the bar mill is concentrated for the hydraulic pistons. It's used from the bars. The floating ball valves. By the way, this one is produced from our production, and We are proud to have this also made in Egypt. The gearbox axis is, we are producing the grades for this one. The hydraulic breakers for the different applications and for the mines, and the anchor bolts for different application also. For the wire, there is a wire rope and BC strands, which is now we can say that there is a booming for producing wire rope and wire drawing, and they have BC strands, which is giving a good results. Also, the applications for this one, which is going for the construction purposes and bridges. If we can speak about the achievements on steel production, we can say that we have to be very care during the production of special steel, because if we are sacrificing some quality items or overdose the cost reduction, then the final product could not be reached to the desired level of quality. We aim to got the cost reduction by segregation the scrap in a very tight and very constrained rules to got a good melting profile. So we segregate the scrap as a stainless steel
2 minutes,
series
Mr. Hammam. 2 minutes.
okay, or 400. It's already divided than each other. The high chromium scrap, the high moly scrap, the high manganese scrap. By this one, we are facilitating the rule for the melters himself to got the final desired chemical. We are aiming now to work on online treatment of rolling mill to achieve the same mechanical properties without going to a post heat treatment. And this is under upgrading now in order to reach the same level without any for the some grades like getting the we succeeded for achieving the impact test by controlling all the parameters on the mill line itself without going for further heat treatment. Also, we aimed to add the boron in certain limits for some grades used for the wire drawing, especially for the high strength wire drawing like IZ1085, which giving a very good results during the drawing process and giving also stability during the treatment after wire drawing, and giving a good results for the final mechanical properties out of wire drawing reaches to around 1670 megapascal. Thank you very much. Hope that I can introduce something about special steel during this short time.
Thank you very much, Mr. Hammam. Really very good presentation, practical from steel plant. I have some question for you. First question from my side. The big challenge for steel producer, especially steel producers, that you have thousands of grade, and every grade need to go to the customer with different shapes, thousands of shape. So this is, and like customers, sometimes they need a small quantity from this shape with this grade to go to this customer, and other customer need something else. How you can deal with this logistic-wise? How you can produce different kind of steel, thousands of grade, thousands of shape based on customer demand? How you can make this balance in production site?
Actually, it is one of the challenge for the manufacturer of special steel. Really, you are getting the harmful point for this kind of production. You are correct. We have a lot of requests, maybe not exceed than 5 ton, 7 ton, 8 ton from one grade to the other. So we are doing like a puzzle, which is taking a long time, keeping that number one, not increase the number of sizes changed during the rolling, which is reached around 55 to 60 change per month, which is huge for any rolling mill, affecting the final productivity. The second thing, that to keep some small stock from each one, which is very difficult to be segregated, but it takes a long time to build your own stock for that. I know building own stock from different grades and different sizes is a very, very tough job, but actually we have to do. We did not succeed, but it's affecting the final productivity. And by the way, the same mill who is producing around 400,000 ton or 500,000 ton of structural steel, the same mill is producing around 150,000 ton of special steel. So this is coming also on the total cost, affecting the final product price.
Thank you very much. Very quick question also from Derek van der Schoorn. He asked if you can kill steel reach to this 15 bm only with adding some aluminum or silicon, whatever, and without vacuum degasser, or you still need vacuum degasser?
No, it still have vacuum degassing to ensure that the total heat already having this one, because adding some alloy, some aluminum or others, you cannot get the ensure that all the heat from the start to the beginning have the same constant level of gases. But by using the vacuum degassing, you are ensured that the heat is still 20 minutes under the vacuum conditions, extracting all the excess gases.
Thank you very much, Mr. Hammam. The third speaker here is Dr. Taha Matar. Also has very famous name in most institute talking about steel. He's a professor for steel technology and ferroalloys in Galala University. Also is the head of Center Metallurgical R&D Institute in Egypt. Dr. Matar is the winner of a state prize in Egypt in 2002 in advanced technology science. He's a professor of material at Galala University since October 2023. He's also head of the Benin Institute in Metallurgical Studies, Ministry Trade of Industrial. Is a chairman of Central Metallurgical R&D Institute from July 2016 to December 2018. Dean Metal Technology Institute from June 2013 to July 2016. Advisor of International Corporate in Misr El Khair Foundation from July 2012 to 2013. Secretary General, founder of Arab Network of Metal Science and Nanotechnology from 2016 to 2019. Is a member of Science Committee of Calibran Institute of International Policies. He's published 141 research articles and 61 industrial research projects. Let's welcome Dr. Matar. So please share your screen.
Yeah, thank you, Dr. Ashraf. Do you hear me?
Yes.
Dr. Ashraf, do you hear me?
Yeah. Yes.
Allow me, because yes, somebody removed me from the Zoom from my laptop. So please allow me to enter again. I'm here from the mobile, so I don't have.
Okay.
Okay.
We'll make you look again. Look again, please. Wait, Dr. Matar. Okay. Look again, and we'll make Mr. Christian start his presentation. It will be last, but log again from your laptop. Stop mobile, because this will create echo. So Jill will deal with you for this.
No. I was closing everything from mobile, only the video. Okay.
Now you are in or not? You can share the screen or not?
No, I'm not in again, because gives me.
Okay. So please log again. Jill will deal with you in background. Excuse me, sir. And we'll go for Mr. Christian. You will be after him. Okay. So let me introduce Mr. Christian now. So we have Dr. Christian now until Dr. Matar finishes this technical issue with Jill. So Dr. Christian Radial has also a master degree and PhD in petroleum engineering, master degree in metallurgical from University of Leuven, which is very famous university in Austria. Christian started his professional career in R&D department in Voestalpine in Austria as a product and process technologist. Later, he was head of sales for special material in Bohrer Steel and the plate mill. In 2008, Christian joined Inteco Melting and Casting Technology in Austria. He assumed role of production manager for steel making equipment in 2012. He was promoted to vice president sales, steel making and non-ferrous. Currently, he's acting as deputy of the CEO in Inteco company. So let's welcome Mr. Radial.
So thank you for the introduction. I will share my screen. Just a moment. Well, thanks again for the opportunity to present some slides about vacuum technology. I would take the opportunity to start with a very, very short, only 2 slides, introduction of Inteco company. We are an equipment supplier and covering more or less the entire process route from melting, refining, casting, rolling, and of course also special melting and remelting technologies. Besides that, we also supply equipment for titanium technology and metal powder production. We are located in Austria. Our head offices are in Bruck an der Mur. We are surrounded by some steel plants in Austria like Voestalpine, Böhler, and so on. We have been founded as a consulting company in the year 1973 and now have developed a complete equipment supplier. We are globally acting with 10 subsidiaries around the world, and to give an impression, with a turnover at approximately 80 to 100 million euro per year. As I said, we are covering the entire production route for steel making, starting usually with the electric arc furnace, and then we have the entire portfolio for refining equipment like ladle furnaces, RH plant, VD, and Tenn plant, which are all degassing facilities. And then we also have in our product portfolio all kinds of casting facilities and then remelting and rolling mill, but I will skip this for this webinar. Of course, this has been also addressed by Ahmed and Professor Iman in their previous lectures, why we are doing vacuum treatment. In the very early days, it was mainly done to reduce the hydrogen content in the castings, which is today still done for the forgings, rail steels or heavy plates. This was the main driving force in the early days. Then there was the invention of these ultra low carbon steel grades, which can be efficiently produced by the decarburization under vacuum to carbon contents below 30 ppm or less. And of course, sorry, just go back one. And of course, the low oxygen partial pressure under vacuum favors the carbon oxidation over the chrome oxidation, which is very important if you are going to produce stainless steel or very high alloyed steel with a very high chromium content. The reason is simply because if you're blowing oxygen to reduce the carbon, if you want to do this under atmospheric conditions, you will oxidize a lot of chromium, which you add as an alloying element. Of course, if you are going to produce a majority only of stainless steel, you might go either for the AOD, and if you are also producing some kind of tool steels or a mixture of steel, then you do a vacuum treatment like a VOD, vacuum oxygen decarburization. And nowadays, a lot of steel grades like interstitial free steel, deep drawing steel, diacods require also nitrogen contents as low as maybe 30 ppm as well. There have been a lot of different degassing technologies introduced over the years. So vacuum treatment has been used already since the early 1930s with some pilot plants. In the very early days, there was a lot of ladle stream degassing, vacuum ingot casting. This is nowadays, this is shown on the top left side. This is nowadays mainly used for large forging ingots. So, I mean, large forging ingots, very large ones. Biggest plants which have been built are around 700 tons. So here you're mainly trying to reduce the hydrogen content. For the integrated mill, which are supplied by blast furnace and then followed by a BOF converter, there is mainly RH degassing or DH degassing. So these are circulation type processes, whereas as more or less state of the art for alloyed or high alloyed steel production are the ladle treatment processes like vacuum tank degassing or vacuum ladle, which we call DTEM process. I will show you later on some slides about it. Or also the VOD, where you combine a ladle tank degasser with an oxygen lens to blow oxygen and to make a forced decarburization. Well, as I said, RH degasser are more used for the integrated mills. So here is one example of a plant which was installed and will be commissioned during 2024. It's a 200-ton RH with oxygen blowing for Istemir in Turkey. So you see very huge dimensions for this 200-ton with 2 treatment stations, a very extended alloy adding system for material handling. And this is one example for a 100-ton RH plant at Föstel MENA in Austria, which we have installed 2 plants over the last decade. So why is the one more suited for integrated mill and the tank degasser mainly used for high alloyed steel grades? There is, of course, an intensive metal slag reaction possible for the tank degasser, which is not possible because you're inserting the snorkels at the RH, so you're only circulating more or less the liquid steel, but without a big slag reaction. So in the tank degasser, you have an intensive metal slag reaction, which is beneficial for the removal of the inclusions or the modification of the inclusions, and therefore improving the steel cleanliness. With the slag, we also have the possibility to have a very good desulfurization during the vacuum treatment. Of course, also a very good degassing efficiency, and we can make a deep decarburization. Usually the circulation type degassers are faster, but the tank degassers are, of course, in the range of the cycle times adequate for the EAF production. So Mr. Ahmed told us about 31 to 32 minutes of treatment time in the tank degasser. This is very good in line with the typically tap-to-tap times of very, very fast electric arc furnaces, which is not in the let's say it's not in line that easy with BOF converters. Therefore, BOF converters usually prefer RH degasser. As we use the ladle also for the treatment, we have lower refractory costs compared to an RH, and the disadvantage of the VOD might be that we need some ladle freeboard to make this treatment. So typically for VOD, we need a ladle freeboard of 1 meter from the top of the metal until the top of the ladle. There exist different types of ladle treatments. The first one, which is shown on the left side, is the DTEM concept, the vacuum ladle, where you do not have a tank, but you simply seal the ladle, which is a special flange, by a vacuum cover, and you're evacuating only this very small volume. This is usually let's say, recommended if you're talking about very small heat sizes, typically for small scale steel plants which are dealing with heat sizes up to 20 tons. So you have lower heat losses during the treatment and a low volume which you have to evacuate. So the vacuum pumps can be also designed in a smaller size. The typically installation in a special steel plant is nevertheless the ladle tank degasser, where you place the ladle in a vacuum tank and seal the entire vacuum tank by a ladle cover, which is shown on the right side. And here we are showing a typical installation for a heat size of 120 to 150 ton installed in a steel plant in Korea. Of course, there are many different design types of this tank degasser, so I just review a few of them. So one is, of course, the heat size. So we at Indeco, we recommend this datum type, this vacuum ladle for small heat sizes, smaller than 20 tons, and the tank degasser for the bigger ones. What can be observed nowadays is that the mechanical vacuum pumps are nowadays the state of the art for producing the vacuum. In former days, it was more the steam-driven vacuum pumps, but at least in the electric arc furnace-based mills, nowadays there is a trend going to the mechanical vacuum pumps. The number of tanks, either 2 tanks or 1 tank, this is more or less completely depending on the required capacity and the available treatment time. If it's a movable tank, or if we are moving the cover, this is mainly dictated by the available space and how to fit in the plant into the mill's layout. The final carbon content and also the product mix, this dictates if you need oxygen blowing lines for forced decarburization, or you only go for a simple vacuum treatment. And the auxiliaries which you're installing on your vacuum plant, like a wire feeder or alloy addition system under vacuum, are mainly given by the product mix which you have in mind. Okay, the vacuum technology is, of course, the key to clean steel. As I said, nowadays mechanical vacuum pumps are preferred, so you do not need any gas-fired steam boiler anymore. The metallurgical results you're reaching, so you can produce steel girts with 10 ppm carbon, nitrogen content of 25 ppm, hydrogen content 1 ppm is usually a target for some. As Mr. Ahmed said, the limit for the specification is sometimes 2 ppm, but of course you tend to be below this to have a very good product. To reach very short treatment times, of course, you have to ensure that your plant is tightly sealed, so you have an effective vacuum treatment. So this is one of the examples which we installed in 2022 in the United States, which I present you some plant components. It's a VT plant for 108 short tons, which are roughly 95 metric tons. It runs with dry mechanical pump. It's a single station with a cover car. You see it on the right side. You move the cover on top of the tank to seal it. Suction capacity 170 cubic meters per hour. Air leaks, we should tend to have it at least below 20 kilo per hour to have a very good degassing capacity. As we do not have an oxygen blowing lens, but doing only vacuum treatment, the freebody is roughly 400 millimeter. If we would have VOD with the oxygen blowing lens, we would go for 1 meter. Pump down times should be lower than 5 to 6 minutes, also in line with what Mr. Ahmed said, that they have pump down time to below 1 torr or below 1.3 millibar 6 to 7 minutes, so that we have sufficient time for the vacuum treatment. Here we see an overview of the plant components. On the left side, the mechanical vacuum pump to produce the vacuum, then there is a filter and a cyclone, because we are sucking off a lot of dust during the vacuum treatment, and not to destroy the vacuum pumps. There is this filter system. Then we have wire feeding for very precise alloying of the melt, and temperature and sampling manipulator to take the samples and measure the temperature at the end of the treatment. An alloy addition system to make alloy addition under vacuum with a vacuum tight sealing. The cover car, and of course the tank as main components of the plant. We have developed over the last year what we call a zero leakage design. So we want to avoid a lot of openings in the cover, which we have to seal during the treatment. So therefore we are going for, you see here, this central socket. During the central socket, we can insert the oxygen blowing lines. If we have an VOD, we can make wire feeding and temperature and sampling measuring only to one feeding point. Therefore, the leakage rates can be as low as 10 kilogram per hour, which allows a smaller design of the vacuum pump, a very short pump downtime, and very low final vacuum pressure. Okay, the key aspects for proper degassing is, of course, the degassing time. It should be as long as necessary, but as short as possible to avoid temperature losses during the vacuum treatment. Of course, the longer the degassing time under deep vacuum, the better, the lower will be the gas content of the melt. And the same is true for the vacuum pressure. The lower the vacuum pressure, the lower the final gas contents of the melt will be. Of course, to reach a very low vacuum pressure, you have to minimize the pressure losses, which we achieve via our zero leakage design, and also to minimize the leakages itself, also design criteria. But of course, this is also maintenance related. You have to do a good maintenance to minimize your leakages on the plant. The steering intensity, you steer with a bottom plug, argon steering usually. So high steering rates, of course, promotes the degassing efficiency. Degassing efficiency is, of course, also influenced by the total surface area. This is something which you can influence to a certain extent. So this is on the one side also dependent on the height to diameter ratio of your ladle, and also then in the end also dictated by the slag, which surface area can be exposed to vacuum to have this good degassing efficiency. The slag condition is, of course, also always a compromise between quantity and quality, and this must be decided from case to case for each sheet and steel grade. To give an example of the degassing efficiency, this is taken from Nucor in Nucor Steel in Darlington, which I showed you before. So here you see the clear trend. The longer you have the degassing time below 1 torr, the lower the hydrogen content will be. So here we see with a degassing time of 8 minutes, we are in a range of 1.5 ppm hydrogen content. Once again, an example from Nucor Steel. Also, steel cleanliness is improved. Here we see an reduction of the inclusions by roughly 27%. So this is due to this very good slag metal interaction, where a lot of inclusion can be separated in the slag. Of course, there is also a modification of the inclusion. This is a topic which is also discussed very broad in the literature. What is the mechanism behind this inclusion modification and inclusion removal during vacuum treatment? What's important if you're talking about efficient degassing, it's of course also the digitalization. Nowadays, it's very essential to have a very accurate process control and process modeling. So there exists process modelings to to simulate or calculate the hydrogen, nitrogen content, and also the temperature prediction, and also to include an alloying model to have an efficient and cost-effective degassing operation. And of course, what you try, you always try to hit your target content as close as possible. And this, of course, helps if you have a very good process calculation. This might also save you some samples in between, so that you do not have to measure in between some intermediate result during the vacuum treatment. So standard deviation for hydrogen prediction is nowadays approximately 0.2 ppm. One tendency is, of course, also not only to have the hard facts on the plant, but also to give some priority to workplace safety. So here we have developed several tools like the automatic gas coupling system, or also robotic solutions. So an example here is a temperature and sampling robot for a vacuum degasser, so that you minimize the operator factor, so you do the sampling always in the same manner, and you not only use some kind of manipulator, but really a robot to manipulate all those samples and to remove as much as possible the workers from the high temperature area around the plant. So coming to an end, show you an automatic gas coupling system. As I said, the degassing efficiency is very much dependent also on a very good steering of the melt during the porous plate at the bottom of the ladle. And for this, we've developed this automatic gas coupling system, where I simply put the ladle on this coupling device. It couples automatically. It has metallic sealing, very high resistant for therefore also suitable for the tank degasser. And once again, you remove any manual worker from the area close to the ladle. Okay, thank you once again for the opportunity to give you this presentation. I hope it was some overview about the possibilities for vacuum treatment, and thanks again.
Thank you, Dr. Christian. This is really very, very good presentation. You went through a lot of practical stuff in a steel plant. Thank you very much. I have one question for you. You mentioned that you guys use bottom version porous plug for steering
yes,
during vacuum degasser. Some steel plant use electromagnetic steering.
yes.
Can you give us a small comment about what is the real difference, and which one you prefer, which technology you prefer, electromagnetic steering or just direct inert gas steering?
So I would say the difference is, of course, there is the share of the bottom steering by argon gas is much higher than the electromagnetic steering. For the electromagnetic steering, you need special ladles. They have to have a non-magnetic part, so that you have the steering efficiency. So the ladles are more expensive. And if you go for a vacuum tank degasser, of course, I don't know any application where they have succeeded to install an electromagnetic steerer on a tank degasser, because you have to be very close to the ladle with your steerer. So usually we prefer to have the argon steering by bottom.
Yeah.
Bottom porous plug.
Yeah. Thank you very much. Do you have because you have this vacuum and this is aggressive movement inside the vacuum degasser, do you see like too much wearing for ladle refractory if the heat going to vacuum compared to if you don't use vacuum?
There is of course in the slide zone there is a higher wear, of course, and therefore also you might use different types of refractories on the ladle, on the metal area compared to the slag area, and of course this is also because the temperatures, if you do oxygen blowing, this can be rather high. So there is also this high temperature wear mechanism on the refractories, of course.
Yeah, okay. So thank you very much, Dr. Radial again. And let's welcome, we have again Mr. Dr. Taha Matar. He's with us again. And welcome, Dr. Matar. You can speak. I already shared your presentation, so feel free to go through it. Yes. And I cannot see you, so just tell me, move in.
Okay. Okay. Thank you, Engineer Ashraf. And I should thank all my colleagues, Dr. Iman, Engineer Hammam, and Engineer Christian. Thank you so much for this valuable presentation. And at the end of this scientific panorama we went through, we will have an overview on the Egyptian market considering this kind of important product, alloy steel. So my presentation about market review of alloy steel supply and demand in Egypt. Actually, I should thank my assistants, Engineer Mahmoud and Hassan, for helping me to prepare this huge amount of, next please, of information. Next, Engineer Ashraf. Next slide. Yeah, next. See, so we will study the what are okay. No, the last one. We will study the industries that use special steels, Egyptian production of special steel, Egyptian imports of special steels, and conclusion. Industries that use special steel, we will go through them. Construction and infrastructure, energy sector, automotive industry, manufacturing and engineering, oil and gas industry, railways and transportation, shipbuilding and marine. Considering construction, the infrastructure, as we see in front of us, they consume low alloy steel and carbon steel. Automotive industries, they consume low alloy steel, tool steels, and carbon steel. Next, please. For oil and gas industries, they need low alloy steel and stainless steel. Energy sectors, they need low alloy steel and stainless steel. For shipbuilding and marine, we need low alloy steel and stainless steel. Next, please. Manufacturing and engineering, mostly tool steel and carbon steel. For railways, as we know, low alloy steel and carbon steel, defense and the military, tool steel, stainless steel, and carbon steel. Next, from this, we can see that most of the applications are concentrating on alloy steel, carbon steel, tool steel, and stainless steel. And we know that most of the construction application are low alloy steel. Next, please. So the Egyptian production of special steel, we have only three main sources for alloy steel in Egypt. The first is Arco Steel, and we had a comprehensive presentation from Engineer Ahmed Hammam. Actually, it covered everything about Arco Steel. We have 100 military factory, Abu Zabal engineering company, and we have our special steel casting foundries. They are our main resources for producing special steel and castings of specials made of special steels in Egypt. Next, please. In Arco Steel, I will not go talk a lot because Engineer Hammam covered everything. They actually cover a panorama, good panorama of special steels like stainless steel, free cutting, spring steel, case hardening steel, quenching, tempering steel, and their annual production mostly 180,000 tons per year. Next, please. Factory 100 military factory. Next, Engineer Ashraf. They produce heavy. Next slide.
Doesn't go.
Doesn't go. Try. I'll speak because I have it in front of me. Yeah. So Factory 100, they produce medium and heavy artillery, production of tank guns, steel, production of special steel, especially weapons steel, alloy steel rolling mill production. They produce 120 millimeter weapon set for M1A1 tank. They also produce rust resistance steel. Next, please. Well, we should know if this production of special steel cover our Egyptian needs or not. Of course not. And we will know now these three resources, Factory 100, Arco Steel, and all the thousands of foundry shops around Egypt. They are producing castings and products made of alloyed steel and special steels. They are not enough for our Egyptian market. And now we will go through what else we have from steel as imports. Well, we will go through the last 3 years, 2021, 2022, 2023. We will see that if we are talking about cutlery, we will divide all the steel products according to the application or the type of alloy. Completely from cutlery, we imported in 2023 $144 million products. It was 123 in 2022, and it was 136 in 2021. And we see there is an increase, annual increase in this from 2021 to 2023. Going to the total pipes imports in Egypt, and we know the revolution in construction in Egypt, thousands of kilometers of roads and infrastructure for new industrial zone. So we imported in 2023 almost $850 million pipe products made of special low alloy steel with annual increase almost 20%. The next, please. Going to the types of base metals as metals. Here we are talking about importing metals, steel that for as we can say raw materials for machining and manufacturing. In 2023, we achieved $130 million imports for this grade. Next, please. Going to the one of the most important imports or needs in Egypt, it is for bridge, cisterns, tanks, wires, nails, and cutlery. We imported during the last 3 years. Every year we import with almost $1 million products every year. Next. Okay. So if we look for the imports for steel for engineering applications in Egypt, next. We have for total weapons, we have almost big decrease from 2021 to 2023, from $16 million imports to $1 million only. Going to the second figure down, if we are talking about metalworking products, it means rollers, machines, all the tools that used in metalworking, whatever it is, forging, rolling, hot rolling, cold rolling, compression, and so on. So, and we know that in Egypt we don't produce roller, and we need to this industry mostly. So we import every year about $1.7 million products for the metalworking industry. Next. Considering the exchanger for fire, we import materials from low alloy steel with almost $117 million every year to manufacture all the body and the casing for exchanger. Considering electrical appliance, we know that all appliances they are made from steel sheets. It is low alloy steel, and the imports decreased from $3.2 million in 2021 to $1.8 million in 2023. Next. I think this one, yes. About the tools for carpentry, and we need in Egypt for, we have a lot of industrial zones working with wood, and most of the machines and the tools are imported from abroad. So almost $118 million are the cost of importing tools for carpenter every year, and it's a huge amount, of course. Going to the machines and the equipment, $2 million imports every year, and it is a huge amount also. Total blades, if we are talking about blades here, we are talking about saws. So saws used in cutting grass, cutting of marble, of granite, of rocks, cutting of paper, of carton, any cutting of plants. So we import products with about 16 in 2023, $16 million. In 2021, $28 million. These blades are mainly manufactured from high carbon steel and high carbon tool steel. Mostly the plates for marble and granite, they are made of the grades C65, C70, C75. Considering boilers and engines and pumps, for the manufacturing, we have many industrial zones in this to produce boilers and pumps in Egypt. So they import the special steels and low alloy steel for the manufacturing of these products. We import with amount of $1.5 million every year from this product. Next, please. Agricultural machinery, about decrease from $350 million per year to $180 million in 2023 imports for manufacturing of agricultural machinery. Considering automotive component, and it is as mentioned most of our colleagues, stainless steel, heavy alloyed steel, and low alloy steel, we import mostly about $1 million products every year. Next. For locomotive and railway cars, we have partial manufacturing here in Egypt. So we achieved this year about $590 million imports from low alloy steel and sheets, cranks, and so on for this industry. Considering we even the cables made of stainless steel for construction industry, for cranes, for all the transportations, we import cables made of special steels with amount of $713 million 2023. It was $513 in 2021. Next, please. For total home appliances, we imported in 2021 with $1,036 million, arrived to $861 million in 2023. Going to the electronic industries and the electrical industries, we have a huge amount of imports of special steels to satisfy the need of these industries, achieved $2.3 million in 2023. Next. For tableware and kitchen utensils, we import with amount of $140 million in 2021, arrived to $61 million in 2023. And I think this reduction due to the problem of hard currency. Other technical and the medical industries, we import about $1.7 million products or materials in 2021, arrived to $1.356 million in 2023. Next, please. Next. Yes. Okay. The last few slides, we consider how many, what is the kind of steel imported. So in 2023, we imported cast steel with about $4.2 or $4.3 million. It was 5 last year, 2022, 5.2, decreased with $1 million in 2023. Next, please. Steel for structural applications, we imported in 2023 with $6.4 million steels for structural applications, and this amount was more in 2022. It was $7.3 million. Next, please. Steel for engineering application, we import with $2 million products. Next. Going to the Egypt steel imports, this figure summarizes everything. We can see that we, for low alloy steel, we import with about $9.5 million low alloy steel in 2023. In 2021, it was $11.5 million. Considering stainless steel, we import almost last year we imported stainless steel materials with the amount of $383 million for tool steels, and it is a big question mark here. We have the possibility to produce a large amount of tool steels, but we import products of tool steel with about $4.3 million a year. Considering if we are talking about carbon steel, it is $2.3 million. For alloys for metallurgical industries, we can see it is almost $100 million imports. From these figures, wait. Last year. From these figures, we started in 2015 to establish something called annual meeting for steel industries in Egypt, steel industry challenges, and every year we call for Egyptian special steel revolution, industry revolution, to have, it is not accepted at all to have only one company, which is Arco Steel, for manufacturing of special steel. We should encourage investors and all with all our power to establish special steel factories and the plants in Egypt. As you can see, we import in 1 year almost $17 million special steels in the year 2023. It was $20 million imports in 2022. So we should move hard in this direction. with the help of our expertise, our colleagues, to encourage the industry of special steel in Egypt. Thank you so much.
Thank you, Dr. Hammam. Really very, very good presentation. And I like also the slideshow way that you have. Is really very good.
No, thanks to my assistant, Hassan. They used to make some good, they are, by the way, we are a steel family. We have a steel technology department full of scientists working only in the R&D of steel and especially steel, mainly going from low alloy steel, achieving stainless steel, tool steel, smart aging steel, triplex steel. Also, we are working on this. Now we are working on new grades of steel for hydrogen tanks and the hydrogen transportation pipelines and tanks. Also, new grades of weathering steel, economic grades of weathering steel. So I should thank my team, my family of steel.
Thank you very much. It's really very good summary about it's really market survey, very good market survey for special steel market in Egypt, and I believe this also we can apply it to MENA region. So question for you, and maybe Mr. Hammam will have another answer for this question after. Do you think, like, if you are an investor, it makes sense to invest in stainless steel producing plant or in carbon steel? What do you think better, Dr. Taha?
For me, stainless steel, but more better than stainless steel, tool steels.
Tool steel, yeah. Low alloy.
I'll tell you why. Yeah. Because tool steels, some of the stainless steel grades are used as tools. So we will have some of the stainless steel with us. Number two, tool steel is so expensive and will give a fast and good profit and return. So the investor will be happy with this. Considering number three, technological wise, if you are producing tool steel, you will produce blooms. But if you are producing low alloy steel and construction steel, low alloy or carbon, medium carbon, you should produce sheets, rods, wires, and this is little bit complicated technological wise, and they will face many challenges in this. So to produce a bloom or pellets, that's something so nice, so fine. There is no this huge amount of plastic deformation and the reduction in area, so they will not suffer a lot. Even the reduction in area will be in tool steels because we produce it in electroslag refining machine, and the electroslag refining machine we got a big bloom, 18 ton. So the reduction will be something like 20%, 30%, nothing more. That's why I go for tool steels. Maybe because I made my PhD on tool steel also.
Maybe. So for Hammam, Dr. Hammam, you work in carbon steel plant, and you work also in special steel. So for you, if as an investor, forget technical point of view, as an investor, do you think it's be more beneficial to go for stainless steel, special steel, or carbon steel?
No, I think mainly the special steel will give a good variety for the market. Tool steel, I do agree with Mr. Dr. Taha also about the need for tool steel, because it's around $4 million per year, which is too much. We can cover. But for stainless steel, the difficulty is coming like there are a flooding from Chinese market and the Indian markets for stainless steel, and the competition between our capability and the capability for the existing plants for stainless steel production in India and Chinese will be very difficult, and can take our efforts. Otherwise, we have the other places that we can go for, like the tool steel, which I do agree with Dr. Taha. For carbon steel, I'm not agree for that, because the low alloy carbon steel, we have already more than 50% capacity in Egypt. So we need to go for that.
Okay, thank you very much. I have a question from Mr. Harun El-Fassi, Dr. Matar. He asked you, those figures that you show in your presentation is represented local transformed steel in Egypt, or is also a statistic reflecting transformed product imported as is in Egypt? I believe you covered
this information from the Export and Imports Authority, and it came from the duties, Gamaric, and it is official numbers considering the imports from Egypt. So this figure represents 6,000 items, collected data for 6,000 items from imports authority, and we just used these numbers and classified these 6,000 items into tool steel, carbon steel, stainless steel, low alloy steel, heavy alloyed steel, and so on. So I don't interfere with the records, with the numbers. I take them from official source, which is governmental official source in the Ministry of Industry, and I just showed it in a nice colored graphs for you.
Thank you.
And it considers only Egypt imports.
Yeah. So question for Dr. Christian Radial. Dr. Matar show us the market survey in Egypt, and this is applicable also for MENA region. Do you think this will be also applicable in Europe? For European market, you still need to have more resources for special steel, and is tool steel is high demand compared of what we show in Egypt with Dr. Matar presentation?
Well, in Europe, of course, we have a very, let's say, a very saturated special steel industry. There are not that many plants which are built new. They are more or less so. In Austria, we have now the steel plant of Böhler, which was commissioned 2023, 2024, which was the first special steel plant built in Europe within the last 40 years. So we see more, let's say, in at least a balanced capacity, if not even to say an overcapacity of tool steels, special steels in Europe. And of course, we are also in Europe faced with these imports from low-cost countries, especially like China, who are now producing also tool steels on a quite acceptable quality, and they are also importing this to Europe. So I think in Europe, the market will develop to even more specialized and demanding grades, but not on a volume-wise basis.
Okay, thank you. We came to the end of our webinar today. I would like to thank all presenters, Dr. Iman, Mr. Ahmed Hammam, Mr. Christian Radial, and also Dr. Taha Matar for this amazing presentation. I personally learned a lot from this presentation, and thanks for all audience for attendance and for the very good question that you asked. We will share, we record already our webinar, and we will share it in our website in AIST MENA organization, and also we will share the presentation in PDF format. So if you have any question, feel free to send to us, to AIST organization, or send to me personally, or if you have the contact of a speaker, please contact them. And thank you very, very much, and looking to see you again for coming webinar with AIST MENA chapter. Thank you very much, and have a wonderful day. Take care.
Thank you.
Thank you. Bye.
Very much. Goodbye, everybody. Thank you. Bye. Thank you.